Today I'm going to present SecureCells, which is a work on a compartmentalization-focused architecture which we tried to build up with security in mind. And this was work done at EPFL between a couple of labs, Hexhive and Parsa. So I guess I could tell you about the motivation for compartmentalization, but the greatest news is that all of you are here, so obviously there's some interest in it. Why do we need compartmentalization? So we all know that modern code is buggy, and it's extremely complex. And a lot of this comes from the fact that you have got third-party code as part of your code base. You have got modules, you have got libraries, and when you're running a browser, you're running JavaScript from some unknown sources somewhere in the internet. So this allows one compartment or one buggy part of your code to compromise the entire application. Compartmentalization adds a layer of defense on top of existing defenses such as memory safety by essentially taking parts of a program and putting them into isolated compartments. They also impose well-defined communication interfaces. Compartmentalization is extremely applicable, broadly applicable, and it applies to browsers, to your server workloads, and also to operating systems, as some of our later speakers will tell you. And it has the ability to mitigate very high-impact vulnerabilities, such as Log4j and Heartbleed. Around 40% of the kernel vulnerabilities can have some mitigations based on compartmentalization. Great, so compartmentalization is amazing and it protects us, but why do we not see compartmentalization everywhere then? Well, part of the problem is that existing mechanisms for supporting compartmentalization have some glaring problems. So first, some mechanisms compromise on security and actually target weaker attacker models which allow it to implement fewer checks. For example, Intel has a popular mechanism called MPK, but MPK suffers from the problem that code accesses are not checked, and as a result, it makes it almost trivial to do cross-compartment code injection. Another major problem are the high overheads of some compartmentalization mechanisms, and this happens. And if common operations are expensive, it means that you cannot have them happening very often. This only allows coarse-grained isolation. And this often happens because mechanisms try to preserve backward compatibility with existing hardware and software systems. Your browsers today already implement some form of process-based isolation, but they have to bear the very high cost of microsecond scale system calls. Finally, some mechanisms specialize for very fixed application domains, which basically implies that a lot of programs cannot use these mechanisms. For example, codomains makes this assumption where it links the instruction pointer to a compartment identifier, and this prevents cross-compartment code sharing. By identifying these pitfalls, SecureCells tries to propose a comprehensive solution which is secure with strong hardware-enforced security checks. We have access control on both the code and data access paths, and we enforce intercompartment call gates to control communication between compartments. We also protect all permission transfers to prevent privilege escalation. For performance, SecureCells make sure that common operations are fast. We implement VMA granularity access control, which removes a lot of duplication of on-chip state, especially in the TLBs, and it allows this mechanism to scale to programs with much larger data sets than current. We also accelerate common operations with unprivileged instructions, which are 1 to 2 orders of magnitude faster than system calls. Finally, we aim to be flexible. We want to support all security policies, and for that, we have a very flexible structure comprising of a permissions table, which I'll describe later, and software operations. So SecureCells does have the ability to provide compartmentalization for a broad spectrum of applications, but it comes at the cost of it requires hardware and software changes in order to be implemented. So how does a program look like under compartmentalization with SecureCells? So let's go into the abstractions. I show out here an example of a program with 5 compartments shown by the different colors. And these communicate among each other and have data regions which are represented by the boxes here. Zooming in into one specific compartment, we see that we assign this compartment to security division with an identifier M. It has access to a few data regions, which I show out here. The green one on the bottom is private to itself, whereas the two other multicolored data regions are shared between compartments. Also, it has a fixed set of entry points, which other compartments can use to communicate with it. So now that I've shown you the abstraction, SecureCells builds its design about three main pillars, two of which I'll describe in the upcoming slides. The first pillar of SecureCells is access control. And SecureCells implements cell granularity access control. That means access control for regions of memory, not individual pages. We have this new structure called a P table, which stores permissions and replaces the traditional page tables. And the P table is extremely flexible. It has per security division, per cell permissions with independent read, write, and execute permissions. For performance, we have also laid out this in memory in a way that is optimized for fast lookups. Finally, access control relies on a per-core MMU, which is able to access these permissions, enforce them, and cache them on chip. The second pillar of SecureCells, which I'll describe today, are the user space instructions, which are available to unprivileged applications. Some of the user space instructions are shown out here. So a core which is executing one compartment can switch to executing a second compartment using a pair of instructions, which is an SD switch and an SD entry. The SD entry, by the way, is how we mark entry points, valid entry points for a compartment. And this helps us prevent inter-compartment control flow attacks. Compartments can also transfer data between themselves. And instead of copying, for large buffers, it's more efficient to transfer permissions instead. And for this, we implement the instructions scgrant and screceive, which are used by the grantor and the receiver respectively. Then, a compartment often wants to drop permissions after it has done something crucial. For example, I show this purple compartment here, which starts with read-write access to a region of memory and later wants to have only read access. We allow this through the scprot instruction. Finally, for multi-threaded applications, a big source of vulnerabilities are data races. When a compartment has exclusive access to a data region, it can reread the data multiple times without any fear of it being modified by anyone else. To enable this, we have the scexclusive instruction, which allows compartments to check whether or not they have exclusive access to data regions. With these instructions, we are able to provide the same operations as are done typically by system calls, but 1 to 2 order of magnitude faster, while at the same time preserving very strict security checks. We also want to talk about SecureCells' implementation. SecureCells can be implemented on both in-order and out-of-order CPUs as per your requirement. The first change that needs to happen is that for access control, we need to make changes to the register file and the pipeline. So within the register file, we have a per-core register called USID, which tracks what the currently executing compartment is. And this can be sent over to the MMU, which then can look into a range-based TLB in order to look up permissions. We also have to modify the MMU in order to interact with a P table instead of traditional page tables. Finally, there are these user space instructions. And for user space instructions, we can implement them through any combination of changes to the pipeline, microcode, or even firmware. We have built an FPGA prototype of SecureCells, which is based on a RISC-V-based in-order core called the Rocket chip. With this design, we were able to achieve 8-cycle switches between compartments, which, when compared to the microsecond scale system calls, is about 3 orders of magnitude faster. We implemented permission transfers through firmware based on RISC-V strap and emulate because it's a very simple microprocessor-like design, Rocket chip. This gives us around 200 cycle latency for permission transfers. But the good news is that when implemented through microcode, we can reduce the cost of this by up to 70%, which brings it into tens of cycles. So this shows that SecureCells' design is, in fact, practical and has amazing performance. So To wrap up, I want to conclude by saying that SecureCells envisions a future of pervasive compartmentalization across application domains. And for this, it identifies and provides 3 key requirements. First, strict security, blazing fast performance, and generalizability or flexibility. We do this through 3 pillars, 2 of which are access control and user space instructions. We have a full hardware, software stack available open source at the URL which I show out here. You can just scan the QR code, and if you have any other questions, please feel free to ask me here or afterwards. Thank you.
Please line up for questions.
OK, so I've got lots of fun questions. Great work. Nathan Doughton, Rice University. So I'm interested in the complexity of your risk pipeline. What happens, how does your context switching work? Do you have like stacks, and do you ever run into like a flush? Because we've done some things where if you have like shadow stacks and stuff inside the pipeline, and it can just create a really big problem in risk.
Thank you very much for your question. So I'll explain a bit about how a switch works. So one of the points which you brought up is context isolation, which is where you have to change one set of registers to another. And we delegate that to software because the throughput of software is going to be identical to that of hardware, because with software, you can essentially saturate the bandwidth between the core and the L1 already. Apart from that, what the pipeline itself has to do when implementing SD switch is 2 things. One, for security, like side channel security, we do a full pipeline flush, which in the RISC-V in-order processor is 5 cycles. After that, it's as simple as just updating this USID register. And that's it.
Thank you.
Thank you.
I have another question if no one's here.
Sure, go ahead.
Go ahead, yeah.
Does this break or just become too taxing if you were to go with an out-of-order processor, just because the flushes would be prohibitive?
That's a great question. So one of the fastest mechanisms which we have available, which we compared to in our evaluation, was Intel's MPK. And essentially, Intel's MPK faces the same problem, is that where they have to flush the entire pipeline before they update the PKRU register. And this can be a bit longer in an out-of-order processor, going up by maybe an order of magnitude, so around 80 cycles. On a 4 gigahertz processor, that's like 20 nanoseconds, which is what the measured latency of Intel MPK is on the lower end. So I believe that A, that is fast enough for user space applications, and B, that is we can have the same performance as MPK on an out-of-order processor because we'd have a very similar functionality in the implementation. Thank you.
All right. Sure, one more question, last question.
All right. Nathan Doughton, Rice University. Very cool work. Can you compare it to ASIDs, PCIDs? Because it seems really similar to the mechanisms, so
yes.
Really exciting.
That's a great question.
Yes. You set me up.
Hey, we are vibing out here. Great. So your current TLBs already have this feature called ASID or PCID based on the architecture, which allows you to have multiple translations from multiple processes within the same TLB and not having to flush every time you switch between processes. We have a similar tagged mechanism when you're actually dealing with compartments, where one of the fields in the range TLB is the the USID. So we actually don't need to flush the entire TLB when we switch between compartments, which is actually essential because you don't want to go through the more expensive operation of reading the P table over and over again. Thank you very much.
Let's thank our speaker again.